Hello everyone, can you hear us now?
Yep, it works.
Okay, perfect. So my name is Katarina and I will be facilitating this workshop today. I represent Innova. Innova is the partner at Extended responsible for the communication and dissemination activities. So first of all, I would like to thank you all for joining us. It's really great to see the interest being done within the project. And during this workshop, the Extended Consortium that is live here at BMZ facilities will be presenting you a clear and structured overview of Extended, from the project goals to the technical innovations that we've been working on during the past 1.5 years, more or less. We will begin with an introduction to the project and its partners, followed by presentations on the battery model concept, cell characteristics, thermal management, battery management system, and next steps. And finally, we will have the opportunity to do some questions. We have a Q&A session that we will open at the end, and we are very eager to hear your thoughts and questions. So right now, we will start to present the overall scope of the project. And I'm pleased to introduce Bruno Rodrigues. Bruno is the project coordinator and works at AVESTA. Bruno brings over 15 years of experience in production and emerging technologies, with a strong track record managing international projects under the European Commission. So Bruno, please go ahead.
Okay, welcome everyone, and thank you for the ones that are here, and also for the ones that are following our workshop online. I will do a brief introduction, and I will leave the juicy part to our experts that will explain everything in better detail. To give you a little bit of context about Extended. Extended is a project that it's aiming to develop the next generation battery pack in this situation for semi-solid state batteries. We are trying to aim to develop a modular and that have new technologies like wireless communication in the BMS area, from new approaches to thermal, and also new concepts in mechanical design, but also taking in advantage LCA to develop. We are composed by 19 partners that they cover, I think, almost every part of Europe and even outside of Europe. That it starts from Portugal with Innova, like Katarina already presented himself, also in Asia, RTO that is giving a lot of support in LCA and LCC. Then we move forward to Spain, and we have 3 partners like Ikerlan, Mondragon, and UPV, Universitat de València, that are tackling from the part from safety to thermal simulation, and they are giving a big contribution for this part. Then we move forward to France, and we have CEA, that it's helping not only in the sensorization of this next generation battery pack, but also in the prototyping of the same. Then we can move to my company, to Belgium, where we have AVI, that we are cell and battery pack producers and manufacturers. And we also have the support for Flanders Make, that it's also giving an important role in the testing and validation of this next generation battery pack. Then if we move to Germany, we have our hosts for this workshop, that is BMZ, that it's a specialist in the battery development. They cover several experts on this point, and they play a crucial role in the development of this next generation battery pack. We are also having the support from Fraunhofer Erlangen, IISB, that it's the partner leading the development of wireless sensors. And my apologies to Lumency that I didn't refer in Belgium, and they are also giving support in the sensorization of the next generation battery pack. Then if we move to Lithuania, we have the support of Solitec with their knowledge in home energy storage, and that help in the use case definition and the part for the home energy storage that I refer. Then if we go a little bit down and then we enter in Italy, we have GVS, that are a specialist in also a part of the cooling of batteries, and they are giving us support in that field. Then if we move to Macedonia, we have AVI Macedonia, our affiliated partner, specialist in BMS, that it's giving the support also in that part. And then if we move, last but not least, if we move to Turkey, we have Axos, Cyro, and Bozankaya. They are specialists from the automotive area. They are specialists in production technologies for battery assembly. And they are giving also, they are contributing in an important way for this perspective. This is a project that it's past its middle life. We are more close to the end of the project than to the beginning. We land in May last year, and it's an interesting project that we encourage all of you to follow. We cover, and in this will be a little bit a teaser of what we are going to talk about. This project covers mainly the development of new BMS approaches, also new solutions for thermal approaches in the battery pack, from simulation to new characterization of the cells primarily, then how to integrate these in a battery pack. That is also helping the mechanical design and the partners that are doing that. And as always, and something that concerns all of us, it's the safety of not only the cells, but also for the battery pack, how it will perform and how we will increase safety standards that we have nowadays. And now I pass the floor for my colleague, Max from BMZ, that will follow up this meeting. Thank you so much.
Okay, so right away, we'll take a closer look at the foundational building blocks of the system, the modules. Presenting this topic is Maximilian Mellin from BMZ Group. Maximilian is a project leader and a lead cell engineer at BMZ Innovation Hub with strong academic background in material science and ongoing doctoral work at THU Darmstadt.
Yeah, thank you so much for your introduction. I welcome you again from Karlstein am Main, from BMZ Germany in the middle of Germany. I want to start with a module and the specification. So it will be kind of a top-down approach. But I will start with our boundary conditions. So how you develop a module, how you develop a battery, you have certain criteria you want to achieve. In this case, we have KPIs defined, so we want to focus on a lightweight design, modular design, and enhance safety against fire. And this aspect we want to take care in different use cases. So we define 3 use cases, namely energy storage, electric cars, and electric buses. So our idea is to build 3 demonstrators for each use case. We took a deep literature review, what is state of the art at the moment. The people talk about lightweight design and plastics. You can see from this graph, even if it's a little bit small, that still the most people uses metal, steel, and aluminum for the enclosure of the battery pack, and only some concepts exist to use plastics. However, we want to take this approach, even if we have high KPIs for our module design. So what is our solution, our selected solution? These are in fact reinforced polymers. So one thing is to have the lightweight design, but of course we also need mechanical stability. These polymers are fire retardant. So we try to achieve the enhanced safety against fire. And this we want to use for the cell holders and for the enclosure. But at the end, we also want to keep a simplistic design, because dismantling and also easy dismantling is in focus. So here I show you some first pictures of our concept. We take our partners and we had our experience together to design different modules. And these were our first concepts. They range from a simplistic design to a design which focus on the high pressure you need for solid state batteries and other approaches. Our new version of the demonstrator put keep the simplistic design. And even if you cannot see so much from the outside, we will look in detail on the parts inside. You can already see that this is a simplistic design. Our new version also includes the enhancement by cooling plate and BMS, which we will discuss in detail later. So how is this demonstrator constructed? You can see here a video of the demonstrator. One is the enclosure, which we open here, and then you can see the steel stack with the cooling plate, with the BMS, and also the pressure plates, the heat shields, and the cells themselves, the cell holders, and the compression pads. All of these components we will discuss in detail in the next parts. So, as I mentioned, we have the 3 use cases. Our focus is on building modules. So how we discuss the different use cases. For this, we focused on virtual use cases. So we scaled up our demonstrator virtually and collected our boundary condition we defined. As you can see here, just to point you out, some KPIs, for example, energy density, fast charging, but also the size of the battery pack. For real life application, you have to consider also crash structures, which you can see here on the pack in green. But we also have other use cases, namely bus and storage. For all these use cases, as I said, we have special design demonstrators, which are more complicated or more simplistic with other requirements for the different use cases. So now we want to look in detail on the different components.
Okay, so for now we move into the heart of the battery, the cell, and I'm happy to introduce Basit Jimoh from CARISSMA GmbH. Basit specializes in heavy propulsion and battery safety, with a particular focus on battery design, recycling, and machine learning applications for safety assessment. Basit, please go ahead.
Good afternoon, everyone. Thank you for this introduction. So I will talk about the cell description, and the cell in question is a semi-solid state battery. So we go to the next point. So for my presentation, I'll be looking at the characteristics of the semi-solid state battery cells. And under this, I will talk about what are solid state and semi-solid state battery cells and why semi-solid state battery cells. And we'll also look at the semi-solid state battery specification. Then we'll proceed to the safety performance evaluation, where we'll look at the behavior under abuse tests. We'll also look at a quick demo of how these cells react to different abuse tests. And we'll take a look into the virtual simulation of the battery pack. So the first question is, what are semi-solid state battery cells? Because most of us are used to the lithium-ion batteries we are all have in the markets today. Then the question is, what are semi-solid state battery cells? So these cells actually use the generation of liquid solvents in solid polymer, while some of them could also use monomers. So in some regards, some people have described these cells as quasi-solid state cells. Probably you might have heard of this. And some of them refer to them as pseudo-solid state cells. So when you hear of the word quasi or pseudo, you are talking about semi-solid state cells. And in some literatures, some of them have mentioned this to be solid state cells, which could be convincing and somehow marketing strategy, because semi-solid state cells, of course, are not solid state cells. And some papers have referred to this as all solid state cells. So this puts into consideration that all solid state cells and semi-solid state cells are not the same. So why have we chosen this particular chemistry or this technology? For the liquid, like the normal lithium-ion battery cells that we have in the market today. We have issue of solvents, which causes the flammability, and as a result, we have thermal runaway. These are common problems we have in conventional liquid-ion lithium-ion battery cells. While for the solid-state battery cells, which are yet to be developed, we have issue of solid interface in these batteries. So the reason why we have the semi-solid state cells is to incorporate the advantage of both the solid state cells and the lithium-ion battery state cells. So in that case, we enjoy both the advantages of conventional lithium-ion battery state cell and the solid state cells. So for the cells that we have in question, this is what the specification is like. We have a kind of breakdown of some of the materials for this cell. For the cathode, we have the NMC, and for the anode, we have the silicon carbide, and we have other information. It's pouch cell, that's 5 amps hour capacity. We also have the discharge curve to the right, where we have the voltage measured against the discharge capacity. Now we move to the safety performance evaluation of the single cell at cell level. So we are looking at this at cell level. So this particular abuse test is called the forced discharge, which some people call over discharge. It is done according to the IEC standard, and the cell at 0% SOC was discharged at 1C rate until we have this voltage of 0.925 according to the IEC, which is about 120% of the nominal voltage of the cell. Then after that, we also try to discharge the cell until 0 volts. So this is the summary of the test of the forced discharge. During the discharge, we observed that the voltage dropped rapidly and was around 0.5 volts after 20 minutes. This test did not result to venting. There wasn't thermal runaway, but there was slight swelling on visual inspection. So this cell passed the IEC standard with hazard severity rating of 2. So we move to the overcharge test. And this test was also done according to the IEC standard. At 100% SOC, we CC charge the cell until the voltage is about 5.04 volts according to the standard. So beyond the standard, we also proceeded to charging the cell until 7 volts to see at what point the cell failed, so we can know the behavior of the cell during failure mode. So we have the summary of the cell and what the cell looks like after the test. There was venting at around 6.5 volts, and there was thermal runaway at 7 volts. The maximum temperature of the cell at thermal runaway was about 450 degrees Celsius using the using the flare camera. This cell passed the IEC standard. However, it failed beyond standard with hazard severity rating of 7. We also did another electrical abuse test, which is called the external short circuit test. So the cell at 100% SOC was short circuited by connecting the positive tab and the negative tab together using an external resistance of less than 5 milliohms for 10 minutes, according to the IEC standard. And we have the summary of the results here. There was venting and liquid electrolyte leakage. From the FTIR measurements, we saw that there was organic solvents, the carbonates, which is the EMC-DC. We also saw a voltage drop to 0 volts during the short circuit. And when the relay of the short circuit equipment was open, we saw a voltage rebound to around the nominal voltage. We also saw increase in the surface temperature in the cell, which was more prominent around the center of the cell and close to the terminals of the cell. According to the standard, this cell passed the IEC standard because the standard stated that the cell should not explode. However, the cell passed the standard hazard severity rating of 4. So the next test is the thermal test to see how it behaves to external overheating. And according to standard, the cell at 100% SOC was heated up with a ramp heat of 5 degrees Celsius per minute until the temperature reached 130 degrees Celsius. The temperature was maintained for 30 minutes. Then afterwards, the cell was overheated. So we have what the cells look like after the test. So during the standard phase, the temperature of the cell was constant at 130. When the temperature was increased or raised above 130 to 230 degrees Celsius at 38 degrees Celsius per minute, we started seeing venting. And when the temperature was raised above 300, the cell exploded. So according to the IEC standard, the cell is considered safe. But beyond IEC standard, which we try to see the failure mode of the cell, we saw that the cell failed at 300 degrees Celsius with a rating of 7. Then we move to the mechanical abuse test, which one of them is the nail penetration test. This test was, however, done according to literature. And as you can see, the cell was penetrated with a nail of diameter 6 millimeter and that speed of 30 millimeter per minute. We have the summary of the test here. There was rapid increase in the cell temperature, spike voltage. The maximum temperature around the cell is a function of the speed and the SOC, which means the faster the speed of the nail, more the temperature of the thermal runaway, and also the more the SOC of the cell, the more the temperature of the thermal runaway. So according to rating, we rated this as 7. So the last test, which is not the least, is the crush test. This was also performed at 100% SOC with a crush impactor, a spherical steel of diameter 7 kilogram. The speed was also the same as the nail penetration speed at 30 millimeter per minute. So according to the standard, we should crush the cell such that we see a deformation of 15% of the cell thickness, or when the force is about 1,000 times the weight of the cell. And according to the summary, we have no temperature increase during or after the crush. The voltage remained unchanged. The internal resistance also remained unchanged. So this cell that you can see in the picture, even after the deformation, we could still measure resistance, measure voltage, and so we classify this as rating 2, which means it passed the IEC standard. So we have a demo of some of the tests. So I'm going to play this. That's the nail penetration. Now we look at overcharge tests. As you can see, there is swelling. Then when the cell was overcharged to 7 volts, we saw the reaction of the cell. And this is the overtemperature test or the external overheating test. We used heat pad controlled in this case. And at failure mode, we have the venting and the explosion to be as much as 1,000 degrees Celsius. So moving forward, we have the results from the different tests. Yeah. So according to the results here, we have the pass and the fail and the ones that have been done to standard. The crush test passed. That's why you have it in blue. The nail penetration was not done according to standard. It was done according to literature. And it has a rating of 7, which means it failed. We have the external overheating test, which so the crush test passed. according to standard. We have the nail penetration, which was not done according to standard. This failed. We have the external overheating test. According to the standard, we have it passed at a rating of 2. But however, when we went beyond the standard, this failed. We have the external short circuit. This passed the test with a rating of 4. But when we went above standard, for the overcharge, when we went above standard, we saw it failed at 7. For the first discharge, for both the standard and beyond standard, the cell was pretty okay. So for the third part of the presentation, we have the virtual simulation. So the results from the experiments was used for the virtual simulation. So in the aim of the virtual simulation is to see how the battery pack can be simulated using the result from the single cell, using the LS dyna. We have the mechanical validation in progress. We have the electrical validation and the thermal validation. So the idea is to see how the different multiphysics finite elements relate from the mechanical part of view, the thermal, the electrochemical, and the electromagnetic, using different elements like the displacement, temperature, Joule heating, and current density. So the battery cell in this that we're talking about is as a main contribution to the mechanical response is coming from the cell stack. The exterior film is very thin compared to the cell thickness and have relative low strength. The cell will be described as compressible foam, whose idealized stress-strain behavior is shown below. You can see the stress-strain behavior of the cell that shows the stress and the strain. And on the simulation part, we have used an homogenized model. And this is more pragmatic than the other model that was discussed in the project. So for the validation of the mechanical test, we use the crush test. And as explained before, we have what the crush test looked like, the impact of the cell. And from the virtual simulation parts, we have this sphere, this holosphere, designed with rigid imposed velocity history of 30 millimeter per minute, just like in the experimental value. We also have the cell that was modeled, which was described as crushable foam, bottom nodes, and also rigid, such that there is no movement around. So according to the simulation, when this was simulated, we have results from the simulation like this. We have the impactor acting on the cell, and we have the effect of the impacts on the cell surface. And from this model, we have the energy density across the cell. So for the abuse implementation after the mechanical validation, we also plan to introduce the failure mode. How can this crush test be implemented virtually such that we have the failure mode? Is either through the internal short circuit from Randall circuit model or from introducing an exothermic reaction by additional heat of source. So I think that's the end of the solid state and semi-solid state battery characterization. So thank you for listening.
So we move on and explore how the project ensures safe and efficient battery operation through thermal management. So presenting this is Carlos Micó, Associate Professor at the Universitat Politècnica de València and Senior Researcher at the Clean Mobility and Thermal Fluids Research Institute. His work bridges experimental and simulation approaches to battery safety, thermal control, and alternative fuels. Carlos, please.
So, hello everyone. What we are going to talk about in this part of the workshop is on the design of the battery thermal management system, which allows the cells that my colleague Basit explained before, allows them to operate properly. So during this part of the workshop, what we are going to talk is about the design process that we have been followed until now in the project, but also on the final decisions that we are already taking in this matter. So we will talk about the concept, going through what are the requirements of this battery thermal management system, what is the design proposed for this battery thermal management system, and some solutions related with the design. And finally, even we will talk about some first proof of concept of the decisions that we have taken during the process until now. So first of all, connecting with what my colleague Maximilian showed before, we have some use cases and some KPIs that define the boundary conditions for our module. These use cases are three different ones: light-duty vehicles, heavy-duty vehicles, bus, or stationary application. And related with also the battery thermal management system, the KPIs that we need to follow are the temperature homogeneity of all the cells, the maximum possible to reduce aging, excessive aging, also the lightweight of the solution, as the total, as the global idea of the final module should be this lightweight solution, and also kind of modular design, which allows to extend or to the scale the solution, the module, to many different applications. So once considering these boundary conditions, then first we addressed a kind of state-of-the-art review in which, well, we identified some battery thermal management solutions which are already quite conventional, like, for example, the air convection, both natural or forced convection, and also the indirect cooling through, for example, liquid cooling plate, but also some others that are already concepts that are easy to find in literature. Our industry is talking about them already, but they are not so common yet, which are like immersion cooling or the use of phase-changing material. So considering the advantages and disadvantages of all these potential solutions, together in the consortium, we decided two different approaches to cover the different applications we are taking into account in the project. One is air cooling, natural convection for the stationary energy storage application, based mainly on its simplicity, but also on the low request of this type of application. And on the other hand, in order to also being able to address a more demanding application like vehicles, we are introducing for those modules an indirect cooling solution based on cooling plate. So once this the idea was taken, then we had to define what are the requirements of what will be the requirements of this battery thermal management system. And for that, we followed an approach based first on a complete characterization of the cell, both electrical characterization and also thermal characterization to obtain the properties like heat capacity or conductivity. And then we use this characterization in order to build a virtual module of the battery, virtual module based on equivalent circuit model, coupled with the thermal behavior of the cell. So it is able to reproduce the different behavior of the cell under different temperatures. So at the end, our main goal is to be able to replicate on one hand side the thermal behavior of the cell, but also the amount of heat generated by the cell, which is what the battery thermal management system needs to deal with. So with this tool, we are able, which is already working, what we are able is to introduce a profile like it can be seen in the left-hand side of the slide, in which we define how much current will go or will be supplied by the cell. And then this current, we can transform it in an amount of heat generated by the cell. So once these requirements are defined and based also in this modeling tool, then we move to the design of the thermal management system. And for that, in this project, we decided to follow a combined approach in which we, on one hand, we use 1D simulation tools, and on the other hand, we use 3D simulation. So each type of tool has its own advantages and disadvantages. So for example, the 1D is much more simpler, is based also in an open modeling architecture, so it's easy to share, it's open source, but at the end, it means that, or it requires to take a lot of assumptions that simplify the process, but also could mean that the results are not as accurate enough for analyzing details. So this makes this type of tools ideas for a quick evaluation of alternatives, but maybe not for the final design. So for that, then we introduced this 3D CFD simulation in which, okay, it's much more complex, it's much, the computational cost is much higher, but at the end we have more detail, both in time and also in space, and also it involves resolving multi-physical equations. So the assumptions that we could make at the beginning, now they are not necessary. Exactly the process that are happening there will be solved. So this makes this tool especially useful for a detailed analysis of the components, and this is what we have used this for. So based on this approach, what we managed to design, so I would say the main core of the thermal management system, which is shared between both the stationary application and the vehicle application, is what we are calling here the cell unit. So at the beginning of the workshop, my colleague Maximilian already shared something about this. I would like to go into a little bit more detail. So what we are calling the cell unit is a joint of different elements. We have the cell, which is the core of this one. But then on the one side of the cell, we will have some kind of insulator layer, which will be the compression part in this case. So this is placed to avoid the cell to share heat directly with the next cells. So to put a kind of thermal barrier between cells. But on the other hand, we need to extract the heat from the cell. So for that reason, on the other side of the cell, what we introduce is a heat spreader, what we call here heat sink, which will help us to extract the heat from the cell and send it to, for example, what we indicate here as the heat dissipation interface, which for the stationary application will be directly in contact with air. So the dissipation will be through natural air convection. But for the vehicle application, what we will have there in contact with that phase is the cooling plate. So we'll have indirect cooling dissipation to help evacuating the more amount of heat that is generated in this more demanding scenario. So then focusing on some of the elements I have shown. So first of all, the heat sink. So for that, in this project, after different analysis with the tools that I have mentioned, what we decided is to go for a solution based on graphite. So why we took this decision, why we are considering this solution? Because if we take a look at the properties that I'm showing here in the slide, in the tables, so what we see is that the graphite solution first has twice as much conductivity as a standard aluminum material that could be used for this purpose. That is quite common in this kind of type of applications. But also at the same time, we can see that the density is less than half the aluminum. So at the end, we will have thinner heat sinks, but that weight less, but also have the same heat dissipation capacity as the aluminum solution. So in fact, thanks to these evaluation tools that I have mentioned before, so we managed to compare different design proposals, and we proved that going for a full aluminum solution, which is quite common due to the availability of thin material, requires a heat sink of 3 millimeters thickness at least. And compared to the graphite only requires 0.5 millimeters thickness. So at the end, it means a weight saving of 25%, comparing the solution using these graphite layers with respect to using only full aluminum solution. Another one of the elements of the battery thermal management system that we have been also evaluating, and we are trying to bring some innovation to the project, is the cooling plate. So in this case, what we are proposing in the project, thanks to the collaboration of different partners, is the use of what we call a hybrid concept. So what's this hybrid concept? So instead of let's say, going for a more common solution based on just single material like aluminum in this case again. So we are going to something that combines a top layer of aluminum, which at the end is the heat transfer interface with the heat sinks that we shown before. And in the bottom, instead of using aluminum, we use a lighter material with, yes, less or worse thermal properties, but in a side of the cooling plate in which they are not necessary. So here again, we have a table in which these properties of both materials, the resin for the bottom part and the aluminum for the upper part, are compared. And in this case, we see, as I said, the conductivity is much worse for the resin, but the density is also much less than for the aluminum. So at the end, with this solution, we can reduce the weight of the module without, and the simulations allowed us to prove that the thermal efficiency of this solution is not drastically affected compared to the aluminum one. So it's also suitable for the application. So at the end, compared to a full aluminum cool plate, we can save up to 10% of weight, and we are still working on redesigning the cooling plate, so the potential weight saving could be even higher than this. Finally, with all these decisions taken, we move to the proof of concept. So basically, what we are doing here is not without the need of waiting to the final demonstrator manufacturing. Within the project, we have built a kind of reduced scale module, taking advantage of some of the decisions that we have been summarizing during this workshop. So we have a kind of setup similar to the one Maximilian showed before, in which we have this cell unit. We have exactly the same elements. Probably the materials are not the final ones, so are more common materials that for making suitable its construction in a short period of time. But at the end, it already represents how the battery thermal management system will be working, and it allows us to evaluate if we took good decisions or not. And I can say that the first results with this proof of concept already shows that we are able, with in load cases corresponding to EVs, demanding cases, with the use of indirect cooling, we are able to keep the temperatures below or 35 degrees even. So we are able to reduce the temperature of the cells compared to the case what we see in purple, which represents no active cooling. And then also, if we take a look to the different curves, we are even able to see that all the temperatures corresponding to the same cooling configuration lies within a margin around 5 degrees Celsius. So it's also both results allow us to confirm that the concept that we are proposing, that we have started testing, is keeping the temperature, the maximum temperature of the cell for a demanding case under a reasonable value, for which we consider it could help us keeping the aging of the cell in a reasonable range, but also it allows us to keep a certain homogeneity between cells within the 5 degrees Celsius, which is quite a standard in industry right now. And then with that, I give the floor to my colleague Matthias. We'll talk about how everything is controlled.
Dive into the brain of the battery system, the battery management system. So I'm pleased to welcome Matthias Hessmann from Fraunhofer, mechatronics engineer by training. Matthias is part of the battery system group and focus on mechanical and electronical development at both component and system level. So Matthias, the floor is yours.
So then thank you for the introduction. Then I would like to come to the electrical solutions that we're working on in the extended project. So in the beginning, I would like to come back to the KPIs, one of which is that we want to have a more accurate temperature estimation by the development of novel state estimators based on the cell impedance, and also for the assembly and disassembly process to make this completely automated, which means a time reduction
which is then directly corresponding to a reduction of cost during the assembly of the module. Why is it even important to have a BMS in a battery system? Maybe I want to come to this very basic question in the beginning. So basically, this is important to monitor the status of the battery cells and to guarantee the safety of the battery system during operation, and also to communicate to subsystems like the battery thermal management system, what Carlos has just presented, but also to control units that are part of the system. When thinking of a car, for example, this might be a control unit that collects the battery information to then see how the charging process needs to be. Okay. Within Extended, we have some innovations, one of which is that we are looking towards a single cell approach, and also that we have a wireless or contactless communication, which is not usual for state-of-the-art battery systems. And we have also foreseen a novel measurement principle, which is the electrochemical impedance spectroscopy, which is not common in state-of-the-art battery management solutions. And also the solutions that are being developed within Extended are both modular and scalable. So at first, I would like to present the architecture that we have developed within the project. On the right side, we see the control and management unit, which is monitoring or collecting the data from the individual sensing units, which you can see on the left. So we have 3 individual approaches. The upper one in orange is the advanced sensor, which I will come back later to. Basically, here we are using a radio frequency communication approach. And the second one would be the impedance sensor, which is communicating via a daisy chain, but we are also using a wireless communication to the first BMS slave. And last but not least, we have the synchronous measurement. The aim of this sensing solution is to provide an optical daisy chain to communicate wirelessly across the complete system, and to also trigger synchronized measurements within the system. The lower layer is a state-of-the-art BMS slave, which is also just used for validation of the developed prototypes, because this is quite new, and to make sure that we can operate our demonstrator safely, we've also foreseen the state-of-the-art battery management system slave. Okay, so at first I would like to talk a little bit about our central control unit, which is the Fox BMS master. So Fox BMS is an open source research and development platform for battery systems. The Fox BMS is capable for monitoring several system level aspects, such as the current monitoring, or also the control of the pre-charge process, and also the contactors, also with the contactor feedback if needed. And we have also the possibility for an isolation monitoring. The BMS master is also used to communicate to subsystems, like, for example, test bench or vehicle control units via CAN, Ethernet, or RS485. On battery cell level, we have the communication to the analog front end, which is also organized by the BMS master, and also the state estimations, such as state of charge, state of health, and also to control the charge equalization process. So now I want to come to the BMS slaves and to the BMS functionalities within the extended project. So
we see a block diagram on the right-hand side, where we have incorporated all the functionalities that we have. So from the control and management unit, we have a wireless and contactless communication interface to the sensor sitting on each individual cell. These monitoring units, the BMS slaves, they are capable of measuring the cell voltage and the cell temperature, and with novel state estimators that are being developed within Extended, also the cell core temperature. Then we have the possibility to measure the impedance of the cell, the force of the cell, and also the force distribution across the cell. I've said we have the possibility to measure the temperature, maybe a bit more detailed. We also have developed a sensor within this work package where we can measure the temperature distribution across the cell. Of course, we also have the charge equalization process. So that means balancing. The communication is with the BMS monitoring units and also to the external subsystems within Extended. This brings me to the first approach that we're using. So this is the BMS slave approach from Fraunhofer IISB. What we see on the bottom right of the slide is the BMS slave, which is divided in multiple sensors. We have for the first cell the first analog front end, which is monitoring the first cell, which means that it controls all the cell parameters, such as voltage, impedance, temperature, and also the balancing. And then we have designed a PCB, a flexible PCB, where we have, as we are building a module, try to make multiple analog front ends on a PCB so that we have we do not take too much space inside of the module and that it is easy to integrate. On the top right of the slide, you can see the PCB which we use for communicating to the Fox BMS master. This has already been tested and validated. Yeah. And on this slide, we are looking at some first measurement results with the sensor I just presented. So on the bottom left of this picture, you see the impedance measurements that we have performed on the extended cell. And we see that the impedance changes with the temperature of the cell. So we use this principle to develop state estimation for the cell that allows us, based on the impedance, to estimate the cell temperature. There we also consider the state of charge of the cells, as this is also a factor that has an impact on the cell impedance, which we can see on the bottom right. So on the bottom right of the slide, you see 2 times the cell impedance measured at the same temperature with different state of charge levels. So this we take also into account so that we have an accurate and valid temperature estimation for this algorithm. The second solution that we are developing within Extended is the optical daisy chain. We can see a picture of the cell and the cell holder, including the PCB that was developed. You see it's very small and it can be slotted into the cell holder. And it measures so the cell voltage, the cell temperature, and also communicates wirelessly via an optical daisy chain with the neighboring BMS slave units and also the BMS master. This is used to synchronize measurements across a complete battery module, which is then important, for example, for impedance measurements on system level. We have currently achieved a data rate of 115 kilobits per second, but this is going to be upscaled during the project until 500 kilobits per second. Sorry. Here you can see the assembly, a CAD model of the assembly, how this is going to look in the end. So all PCBs are in line of sight and can communicate with the optical principle. On the bottom right of the slide, you can also see a picture of the communication with two smart cells with a shared centralized clock signal that is regained on each single BMS wave. The last solution that is being developed within Extended is the printed sensor. So this is an advanced sensor which is printed. So we have different force sensing sensors on this printed sensor and also different temperature sensors. We glued this sensor, which is the orange part here, onto the battery cell. And so this gives us opportunity to measure these values across the cell. So we have a detailed picture on where hotspots of the cell are during operation, and maybe also where pressure is higher. This would mean that we have some local expansion of the cell, for example, or this could mean this. This sensor is communicating to the data acquisition unit, which is the green PCB on top. And this PCB is then wirelessly communicating to the Fox BMS master within the project and also within the demonstrator. And that would be it from my side. Thank you very much.
So to wrap up the technical section, we will look ahead at how the project results can be further exploited and applied. Speaking on this is Willar, co-founder and senior consultant at Tech Concepts. Willar brings more than 15 years of leadership in EU-funded R&D projects, sustainable mobility policy, and solid-state battery innovation. Willar, please go ahead.
Thank you, Katarina, for introducing me. So yeah, we have seen impressive results, I think, today. And actually, that's what I like very much about this specific project, that we have very tangible results. And today, this workshop is rather digital, let's say. But actually, what happens already over the last year in meetings is that the participants, they actually bring physical results to the meetings, and they go around the table. So actually on my right here, we have a table full of physical results. So for example, the sensor of lumency we have just seen presented, it's lying here on the table. And that's something I think is notable, and is also something that we can be very proud of as a consortium and as a project. However, these results, they will achieve probably TRL 5 or TRL 6 at the end of the project, all of them. And that means they reach, let's say, prototype phase. That also means you cannot buy them yet. They need to be mass produced, and then somebody has to sell them. So they need to reach market. And there's still a road to go. And that's what we call, in European Commission terms, exploitation of results. How do we make sure that in the end, after the project lifetime, there's a life for the results, that they actually reach the market? And there can be several exploitation pathways that you could take for reaching exploitation to the market. And that's, for example, scientific, and making publications, or doing new research projects to take them to the next level, and also, of course, commercial pathways. And this is what we try to assist the project with from our side, from Tech Concepts side. And well, what we try to do in doing this is putting the all partners on the stage.
And we have what we call a partner-centric, but also a collaboration-centric approach for doing this. So what we actually do is we organize team building activities just to make people collaborate with each other, come from behind their laptop, actually talk with each other, exchange. And that's also what's needed if you want to collaborate after the project to bring your projects further, because we all need each other. We might need other stakeholders as well. And that's what we do. We try to support this collaboration also in a fun way. So you see team building activities, but we also have workshops to work on the exploitation plans. We have a 4-step approach for that we take, which focuses on all levels you can think of. So there's a more technical level at the downside, looking at the results itself, the key exploitable results, but also at developments from others. What are others inventing, and is that threatening our invention? And also on a social level, we have partners inside the project, but we might also need partners outside the project or stakeholders to be aware or buy our results, so that we have to collaborate after the project. And so you also see that there's internal and external project component to the exploitation. And we take different steps, take the partners by the hand, trying to support them in developing ideas around this. Because exploitation is, for some of us, it's like daily practice. If you are in a commercial business, it's daily practice. You always have to make sure it earns itself back. But not all partners, not everybody at this table here today, for example, has that daily mindset. If you are a researcher, then your daily mindset might be others. And by helping everybody, we try to make sure that our results actually in the end reach the market. Now, I talked about, we put the partners on the podium in our approach for exploitation of the results. But I would also like to put our audience on the podium because we have a few questions for you. So if you can proceed scanning this Mentimeter, then hopefully you can join us and share your thoughts with us. I think we will start with some simple questions, and then we will follow with some more tendential questions, which might also get us started for, well, the talks after this meeting. So I'm now switching to the Mentimeter, and there we go. So let's see. I see that people are starting to get in. Yes. All right, so we have 7 participants. Is there any more joining us? Is it working with the QR code?
Yes.
Yeah.
Just pasted the link for the Mentimeter in the chat.
All right. Well, then I will just give you another minute to scan the code and join us, or you can also go to menti.com and use this code to join us. I talked about being proud of the results. I think a second thing I still want to mention is that we can also be, as a consortium, be very proud of the collaboration. What I have seen, I'm not in the technical developments in this project, but what I have seen is if people get stuck in their technical development, somebody else stands up, says, hey, we might be able to help. And without budget, there is help offered. And I think that's something I would like to stress, that's something we can congratulate this project with a very good collaboration. So I hope, meanwhile, we have some participants in the Menti. I see thumbs up, so that's good. So the first question is rather simple. We were wondering how much of the information we showed today was new to you. And I'm talking about the results that the project is producing. How much of those results you have never heard before of? How much was new to you? And of course, there's also some project participants in the game today, but still we are curious for your thoughts. So we are collecting answers. We are at 17 out of 31. And a thumb up. Is there any more answers coming in? I think we're getting a bit stuck. Well, you can still send in your answers while we are at the next question. So I will go to the next. So the next question is also a simple question. We are wondering which topic shown today you would like to explore more in depth. And you are allowed to put more than one answer. So you can actually tick more boxes before you push the submit button. Well, I'm happy that there's quite a balance because I think what we are achieving is also balanced. I mean, BMS, thermal management, the modular design, it's all very impressive and novel, I think, what we're doing. So, all right. But Basit, I think you impressed the people today, eh? With your evaluation of the solid, semi-solid cells. All right, we will go to the next question. And that's actually about you. So we would like to learn what type of organization you are representing, so that we know a little bit how we can connect answers with types of organization, how several types of organizations look at our world, let's say. So yeah, I was expecting quite some academic community. Also looking at our guests, I'm expecting some students. No policymakers today. So far, at least. The groups you see here are also the target groups we have identified for our project as stakeholder target groups. So this is for us also a way to find out a bit which type of people we are reaching with this workshop. And we still have some work to do in 3, or let's say 4 target groups we can see. Okay, thank you for answering. So the next question will be a little bit more pushing you already. So this is not a question, this is only a presentation slide. I think we have also shown today that we are studying different application areas for semi-solid state batteries. And before we chose semi-solid state, we also looked at solid state itself. And well, we have studied several application areas, but also several technical issues with these cells. And there is a recent publication on this. If you scan the QR code later, maybe, or follow the DOI, you can open it. But we are wondering also what your view is on the application area of solid-state batteries. Where do you think they could be best applied? And that's what the next question is also about. And then I'm talking about European solid-state batteries. So that's let's say, hopefully a near future. But when they come to the market, where do you think they can be best applied? And you can give more than one answer. What do you think that those solid-state cells from Europe can be applied in electric vehicles, that will be the market for them? Or do you think, no, European cells will have a smaller market, they will only appear in niche? We are really wondering how you look at this. Oh, there are still some clear winners here. And no other, that's also. All right. I think we had most answers coming in. Well, I told you that we will be a little bit tangential, maybe. The next one will be, I promise. But it will also be the last one. So, BBC published an article in the beginning of this month, actually. And it's about, first of all, sodium-ion batteries, so salt-based batteries. And it explains a bit about how the situation is in the global market, and that Kettle announced that they plan to mass produce sodium-ion batteries for heavy-duty trucks and cars. But they also discuss a bit about all solid-state batteries. And what they say, or what one of their specialists says, it's that the biggest difference between companies in China and other countries is that China can bring technology much faster to the market. And one of the reasons they say is that the technologies that they bring to the market, they can lean on their current industrial chain. And for all solid state, they say there's some difference because of the solid electrolyte. So it's a different process. It's difficult, so you can rely less on your chains that you have standing. They have cells on the market, solid state. So one could ask himself, should we invest in developing solid state cells in Europe or not? And the next question is, actually, what battery technology can Europe reach the biggest global impact with? In other words, if we invest money in Europe, which technology should we invest in? And you are free to choose words. You can send in one word or two or three. And as inspiration, we also gave the strategic actions from the research and innovation agenda of the BET4EU from 2024. And there is several strategic action directions. So liquid electrolyte lithium ion, so the regular lithium ion, but also solid state. But also you see an action around post lithium ion for mobility. You see flow and aqueous batteries for stationary applications and sodium ion. But maybe you think sodium ion is the way to go, or maybe you're working on something really exotic and think that's really the thing, or you're a fan of redox flow batteries. And we're just wondering, what is the way to go for Europe? And take your time to type, also take your time to take inspiration from others. But this is what we are really wondering. What do you think European money should be invested in? Because obviously the research agenda has taken a direction, and also when you look at the European funding, directions are chosen. We all, I think people here are aware of the calls present. So sodium ion is a big thing, but we also now see too metal air is appearing, and there's several options for metal air, of course, or a lot. I think we have not discovered all the options yet. So that's becoming a nice wordle. We are at 16 replies at this moment. Okay, now things are getting a bit small, but that's also nice. Also lithium ion, so the regular thing, still investing in it. Is there anybody in the room still busy with typing? No? All right, well, I will leave this one open so you can still keep on submitting. And Max, if you can support me, back to control this one, I guess. Yeah. So then I would like to thank you for for your attention for this part of the presentation and for your feedback. And I give the floor back to Katarina, I think.
Okay, so maybe we can do a round of applause to all the speakers. Okay. Okay, so now we open the floor for questions and reflections. Leading this final session are Maximilian and Bruno. So I know that we already have some questions in the Q&A section. Okay, so the first one was already addressed. Max, do you want to read it?
I think this first question was, what is the energy density of the hybrid system and which cell chemistry was evaluated? So this is a really good question. So with cell chemistry, we normally focus on the cathode side. So in this case, it was NMC. As you know, we talked about the cell chemistry before. The thing is that NMC and NCA are still the most interesting chemistry if you want to boost energy density. And of course, they compare directly to LFP, which has less energy density but higher safety. And the semi-solid state technology is really an idea to use high energy materials, but combine it with material which create more safety. So I think we answered the values for the cell. For the pack, we aim to, for the virtual use cases, we calculated up to 210 watt-hour per kilogram. So of course, we have a cell with high energy density, but also with our simplistic design and our solutions, we could achieve a high energy density on the pack level. Another question was what pressure that you can apply for your clamping design. This is also an excellent question. We expected that the solid state technology, as known from literature and results from labs, use extremely high pressure needed. So one of our concepts created a clamping system which allows to have really high pressures. However, in the case of semi-solid, we only need smaller pressures up to 40 kilopascal. What is important here is that our design uses compression pads. So what is in general important for every module design is not only to think about the pressure at the beginning of life, BOL, but also at end of life. And this is an important part of designing the module, but I didn't go into detail into it. There are different solutions. For example, building stronger pressure plates or using compression pads. In a sense, this is a combination of our solutions because you have to track aging, for example, by impedance and others, and then you can find a good solution concerning the pressure. For concerning the cooling plate and our materials, we already answered this material shortly, but maybe our specialist could answer this in detail.
Yeah, sure. So that's a really good question. So at the end, if you want to use these different different type of materials, one thing is the joint. So in this case, we are screwing directly our design screws directly the aluminum plate over the resin part. One hand, it has the main benefit is that it's easy later for dismantling it. So regarding our objectives in the project related with sustainability and so on is better. But at the same time, one key aspect that we need to pay attention is to a proper gasket in order to avoid any leakages, and this is on what we are working right now.
Thank you, Carlos. We have another question in the chat, which asks how can ICE impedance-based temperature sensors work if the cell age differently, also at lower SOC? Maybe this question is a little bit confusing. So we have impedance sensors and temperature sensors, and details on this question will give our specialist Matthias.
Yeah, thank you. It's also a very good question. And as Matt said, has already mentioned, we have both the temperature sensor and impedance sensor, but also for the battery cells, we know the state of health of each individual battery cell, as this is calculated and tracked independently. And based on this, we can calculate the aging of the battery cell and then use this information to improve the temperature estimation based on the cell impedance. So basically, as there is an dependency from state of charge, there is also one from state of health. But as we track this and calculate this for every battery cell, we know the impact and then can adapt the temperature.
Yeah, thank you. Or maybe it should be mentioned that impedance could be a direct measure of the SOH, so the growth of the solid electrolyte interface, but also hindered kinetics or hindered charge transfer will directly influence the impedance measurement and the SOH.
Thank you all for your participation in today's workshop. Special thanks to all our speakers for their brilliant presentations, and to all the partners working behind the scenes that help making these presentations. We just want to say that this is for us the first workshop. We will have a second one, and we will disseminate it in our social media. So please make sure that you follow us. If you have any further questions or feedback, feel free to reach us out. And of course, we will be sharing the recording and materials with you very shortly. So until next time, thank you again and have a nice day.